Hi everybody, this is Math 024, Module 3, Video 2, where we're going to look at functions, definition, domain, range, and graphs, and we'll split this up into two videos, parts 2 and 3 of Module 3. So we're going to start off with some terminology, and the first terminology or term we're going to look at is a relation is any set of ordered pairs. So a relation is any set of ordered pairs. And remember, an ordered pair looks like this. It has two numbers separated by a comma, so that would be an example of an ordered pair. The domain of a relation is the set of all the first components of the ordered pairs. So generally, when we have ordered pairs, we have an x and a y value. They're not always x's and y's, but mainly they are. So the first value, so generally the x values, and then the range of the relation is the set of all the second components, or generally those y values. Now, a set of ordered pairs is a relation, but we're going to look at a certain type of relation. We're going to look at functions. So a function is a specific relation in which each of the first components corresponds to exactly one second component. And as we go through the notes, you'll see more about what this definition means. Just reading it and looking at it now, it's a little bit fuzzy, I'm sure, for some of you, but I promise you we will work it out and you'll understand it perfectly by the end of the videos. Okay, so now we're going to take a look at a relation that we have here. And we're going to list the domain, the range, and decide if it is a function or not. So again, remember, domain is all of the first values in your ordered pairs. So our domain here is going to be 0, 4, 3, and 10. And if you do have numbers that are repeated, you only list it once, but we didn't have any repeated this time. And then my range is going to be 2, 5, 7, and -1. Now, is it a function? Remember, the definition of a function is a specific relation in which each of the first components, or each domain, corresponds to exactly one second component, or one y component. So what I like to do is kind of look at the relationships. So I know that 0 corresponds to 2, 4 to 5, 3 to 7, and 10 to -1. So if I look at this, each domain has exactly one range, or one y value. Each x value has exactly one y value. So is this a function? And the answer is yes, it is a function. All right, let's take a look at letter B. So our domain here is going to be -3, 0, 5, and 1. And then our range is, 2, -2, and then we have 5 that repeats twice, but we only have to write it once. All right, now to see if it's a function, let's look at our domains. So -3 corresponds to 2, 0 corresponds to -2, 5 corresponds to 5, and 1 corresponds to 5. So is it a function, yes or no? And remember, our definition of a function says that each first component corresponds to exactly one second component, or one y. So each x has exactly one y. And if we look here, each of my x values goes to exactly one y value. It just so happens that 5 and 1 both go to the same number, but that's okay. So yes, this is a function. Here's how I think about it. I look at the domain as, if you kind of think of it this way, they are people, and the range, think of them as rooms. So we can have 2 or more people in the same room. So my x values can go to the same y. But if I have an x value or a domain that goes to 2 different y's, so let's say, and I'm just making this up, but for instance, if -3 went to 2 and -2, I can't have a person be in 2 rooms at once. We're not Harry Potter. We don't time travel. So that would make it not a function. But it's okay if our x values go to the same y value. So hopefully that helps explain it a little bit. All right, we're going to do one more here. So we're going to list again our domain, and it would be -3, 0, and then 5 is listed twice, so we're only going to write it once. Our range is 2, -2, 6, and then -2 is listed twice as well. So let's look at our relationships here. -3 goes to 2. 0 goes to -2, 5 goes to 6, and 5 also goes to -2. So now when we look at it, again, we've got people up here, rooms down here. Can I have number 5, who, think if it was one person, can they be in 2 different rooms at once? Hopefully you're like, no, that can't happen, and that is true. My x value has 2 y values. It can only have 1. So is this a function? No, it is not. Okay, so, and here is our last one that we're looking at. It's just written out a little bit differently. They didn't really give us ordered pairs, but they gave us a number grade and a letter grade. So we are going to look at this as the first part is our domain. So the first part is always your domain. So our domain is 95, 81, and 73. Our range is A, B, B minus, and C. And then the nice thing is they drew the lines for us so we can see. 95 goes to an A, and 81 goes to a B and a B minus, and then 73 goes to C. So think of, again, the first part, they are the people, and these are the rooms. And again, it's just an analogy to help you remember. They aren't really people in rooms. But can 81 be in 2 places at once? Hopefully you're saying, no, this is not a function because my x value of 81 has 2 different y values, and that makes it not a function. All right, next we're going to look at function notation. And this is where it gets a little tricky. Sometimes with functions, because they're different than what we're used to seeing. So function notation can be noted as, instead of like y equals, we do f of x equals. And that f of x means that y, it's the same thing as y equals, but it's y is the known dependent value, and it's dependent upon x. So whatever we put in for x. So really, this is function notation down here. So it's telling me we already know that this equation is a function. So it passes, that each x value has exactly one y value test. And so instead of y equals, they put f of x. But that x right there is really just, it's a function of x. That's what it's called. Now, when you see something like f of 2, okay, what it means is wherever there's an x in the equation they gave you for the function, you plug in whatever's in here. So we're just going to do, 3 times 2 minus 4. So we're going to evaluate the function at 2. So then we'll do the math. 3 times 2 is 6. 6 minus 4 equals 2. And then we can try another one. So they want us to evaluate the function at -3. So f of -3 is equal to 3 times -3 minus 4. 3 times -3 is going to equal -9 minus 4. So we'll do plus a negative. We're going to end up with -13. And that would be our final answer. So f of 3 is going to equal -13. Let's look at b. So we have g of x. So the function of g at x is equal to -7x squared plus x. And they want me to evaluate g of 3. So again, what I'm going to do is I'm going to plug in the 3 wherever there's an x in that equation. So I'm going to do -7 times 3 squared plus 3. And now I'm going to have -7 times 9, because 3 squared is 9, plus 3. So -7 times 9 is -63, plus +3 will give me a -60 for my final answer. And now we have to do g of negative 4. So I'm going to do negative 7 times negative 4 squared plus negative 4. Negative 4 squared is 16. So I have negative 7 times positive, not negative 16, but positive 16, because negative 4 times negative 4 makes that positive. And then plus our negative 4. So negative 7 times 16 is equal to negative 112 plus negative 4. So my final answer is going to be negative 116. And that's it for evaluating those. We're going to take a look at a couple more on the next page. All right, and now we are going to evaluate some more functions. And for the next one, they give us h of x is equal to 3. So if you notice, there's no variable in that math problem. So this one, it looks really hard and it looks odd to your eyes, but it's very simple to do. So really, because h of x always equals 3, then h of negative 5 is always going to equal 3, and h of 1,000 will always equal 3. Because this is basically like a y equals equation. So remember, when your y equals, like if you have the equation y equals 3, in your ordered pair, y will always be 3, and x can be any value you want. And when you graph it on the coordinate plane, if you recall, it's going to look like a horizontal line, so it would be horizontal, and that would be y equals 3. So you can see the x values can be anything, which remember, this is our x-axis here, that's our y-axis, and the y value is always 3. So that one, a little bit different, but not bad. Okay, now let's look at D, and this time they gave us the function p of x is equal to negative 4x plus 2. And they want us to find p of a. So all they did here is they didn't put a number, they put another variable. So now when we do p of a, remember, you replace the variable in your original problem with whatever's in the parentheses. So now my problem is going to be negative 4, and instead of x, I'm going to put a plus 2. And that's it for that one, because I can't do any simplifying. I can't combine like terms because there aren't any. So we're done. Next, for p of b plus 1. That one, we are going to have to do a little bit of work, because again, I'm going to plug that in for the x up here. So I'm going to have negative 4, and instead of x, I'm going to have times b plus 1, and then keep my plus 2. And now, to simplify, we can distribute. So it becomes negative 4b minus 4, because a negative times a positive is a negative, plus 2. And then we can finish it off by combining those like terms, negative 4 plus 2. So we'll have negative 4b, and then negative 4 plus positive 2 will give me a negative 2. So that will be my final answer for that one. So again, a little bit different, a little bit of work to do, but in the end, not bad. It's just getting used to looking at it the right way, and not letting that t of x or p of x or h of x scare you. All right, now we have t of x equals the square root of 5x minus 1, and they want us to do, again, t of a. So we're going to do t of a. Again, that just means we're going to have 5a minus 1, and there's nothing we can do to simplify that, so we're all done with that one. Now, t of c plus 2. When we go to plug that in for x, we're going to have to, again, do our parentheses like we did for d. So it's going to be 5 times c plus 2, and then minus 1. So we are going to distribute. So it will become the square root of 5c plus 10 minus 1. And then when we simplify that, 10 minus 1 is 9. So we'll end up with the square root of 5c, and that's not a c. There we go. Okay, 5c minus, or not minus, but plus 9. And that will be our final answer.
All right, so in the beginning, we were given ordered pairs and asked if they were a function, and we could look at the relationship between the domain and the range to figure this out. But now, sometimes we're given a graph and we're asked, is it a function? So one way to check to see if a graph is a function is to do what we call a vertical line test. And remember, a vertical line goes straight up and down like that. It's a little bit straighter than mine, but so if the graph of a relation passes the vertical line test, then the relation is a function. So a relation passes the vertical line test if no vertical line can be constructed so that it intersects the graph at more than one point. So if I look at this, if I look at the first one, when I'm drawing those vertical lines, my vertical lines are hitting that graph. When I say graph, I mean, our line right here. It hits it at only one point. It doesn't hit it more than once. So A is a function. So is this? It is yes. But if you look at B, right away when I draw that vertical line, notice it hits the graph here and here, both at the same time. So because that vertical line hits that graph more than once, that means no, it is not a function. Because think, here x is probably like 1, and it has a y value up here and a y value down here. So it can't be that way. Your x's, remember, can only have one y value. Now look at C. What do you think? Hopefully in your head or out loud you're shouting, oh, not a function, not a function, because look, it doesn't pass. So that would be a no. Now for D, this one, it's a little hard to see, but even when I go right there at the bottom of that graph, none of those vertical lines hit the graph at more than one spot. So D it's an absolute value function, but it is, yes, it is a function. So that's the shape of an absolute value graph, that V. Okay, so now we're going to practice looking at graphs and giving the domain and the range of each, in this case, relation, because if you notice, like A would not pass that vertical line test. But your domain and your range, again, remember domain is the y or the x values, range is the y values. So if we're looking at this graph, remember the horizontal line, that's your x values. So if I notice on this oval that we have graphed here that the x values go from, it looks like -2 all the way to 2. We have x values. So if I write that and I write it in interval notation, we're going to put brackets because it does include -2 and it goes all the way to 2. So we're going to put brackets around that. Now for the range, if we look at this graph, our range goes, it looks like, all the way from 3 on the y-axis down to -3. So again, our range, and you're always going to write it kind of like the number line, so the negatives would go first, the positives would go second, because that's the way it would look on the number line. So from -3 to 3, and we put those brackets around it because it does include those numbers. All right, if we take a look at B, so look at your x values. Again, hopefully you're looking at that and you're like, okay, well, starts here and is here for my x values. So that's -3 to +3. Now y values, you kind of have to like draw a line here to see how far does it go. And hopefully in your head you're like, ooh, that looks like -1 to +1. So those would be our domains and range. Remember, range is the y values, domain is the x values. Okay, now you will find that C and D are a little bit different than what we did before. So remember, domain is our x values. And for this, it's an absolute value graph. And if you notice on the graph, and again, my pen won't draw very straight, but it has those arrows there. So that means it's going on infinitely on both sides. So that graph is going to keep going on and out. So when you see that, if you notice that covering that x value, like I can always find an x value, especially if it keeps going on and out. So for this one, for an absolute value graph, for a normal absolute value graph, your domain is always going to be -∞ to positive infinity, because it's never going to end, and it's never, it's always going to cover that x-axis. Those arrows show that. Now, when we write the domain and we have infinity, we only put parentheses around it because infinity is not an actual number. It's just a symbol. Now, our range, if we notice, if we look at the y-axis, it starts right here. Doesn't include any of those negative numbers, but then because it keeps going up and out, it will go on infinitely. So our range here is going to be, we're going to put a bracket because we know it starts at 0 and it includes 0, but then it's going to go on infinitely. So we're going to put that infinity sign, that 8, kind of sideways 8, and then a parenthesis around that. All right, now D is another one where we have those arrows and they go out, so it's going to go out forever. So this one, and this is where it's kind of hard to visualize. The more you practice, the better you'll get. But for this one, again, the domain is going to be negative infinity to positive infinity. And then your range, if you notice, it covers all the way down here, but it doesn't have any of this top part. So it looks like it starts at, or it goes all the way up to 2, but then it goes down to negative infinity because it goes down to those negatives. And remember, you want to put the negatives first and then those positives. So it would be a parenthesis, negative infinity to positive 2. All right, we have our last two to look at here, and the first one is going to be a line. So it's graphed, a linear equation is graphed here. Your domain, again, we have those arrows that goes on infinitely in either direction. So your domain and your range are actually going to be the same for this one. It is going to be negative infinity to positive infinity, and then also the range will be negative infinity to positive infinity, because anywhere we pick on this problem, we can find a point. Like if I pick right here, if I pick y is -4, I can go out and find a point on that line. If I pick, let's say -5, I can pick a point and find a point on that line. Now for the last one, this one, it looks a little goofy, and it's not touching that line there, but it's riding right along it. But again, it goes on infinitely, up and down. So it's going to be the same as our line next to it. Our domain is going to be negative infinity to positive infinity. And our range is also going to be negative infinity to positive infinity. And again, some of these, it's hard to visualize, but the more you practice and the more you see them, the better you'll get. So don't stress if you're not perfect at it in the beginning. Again, the more you practice, the better you'll get. And this is the end of the first video on functions. It's module 3, part 2, and we'll get module 3, part 3 out to you shortly.